Okay, so we are talking about Baire's category theorem. Now, why is it important? Well, there's a very important theorem that says if A is a perfect subset. Well, this is actually a corollary of Baire's category theorem. So it's very important. If A is a perfect subset, meaning that it has no isolated points. What is an isolated point? An isolated point is if I have a point in the set, I can draw an open ball around that point. And that point, and there's that point in that open ball, there's other points in the set in that open ball. That is isolated point. Well, actually, there's no other point in that set. Let me start over. An isolated point means at that point you can draw a ball around that point, and it has no other points in the set A other than the point itself. Very important. So, and also a perfect subset is closed. So, if A is a perfect subset of a metric space M, then A is uncountable. So, this can be used to prove many things are uncountable. Very important, proving things are uncountable. An example of something that's uncountable that I can prove is the real numbers. But you know, Baire's category theorem, very important. But whenever you think about the real numbers, you should always think about Cantor's diagonalization process. The diagonalization argument, one of my favorites. I remember I was at, I invited one of my professors to the faculty night. Professor Taiping Liu, brilliant mathematician. First thing he showed, one of the things he showed me on a piece of napkin was Cantor's diagonalization argument, because it's so important. But one of the things that I regret is that I spend more time talking about definitions, because that's what he had to study, definitions. But I don't have time to talk about proofs, because I feel that proofs are long, lengthy, and I'm very bad at them, but I have to work on them, and also I spend time thinking about them myself. So instead, let's just do a really quick proof. First proof, the Cantor's diagonalization argument. Why real numbers are uncountable. This is a proof by contradiction. So let's suppose that the real numbers are countable. But you know that the real numbers are countable if there's a mapping from the natural numbers to each element of the set. So you can think of this as a sequence. Let's assume that there's a sequence in which this is possible. So x1 equals point. Let's say x1 equals point. Let's see, x1, x11, x12. X2 equals x21, x22. If you've seen matrices, you're familiar with this. This is what they look up through, and it keeps on going. So in the Cantor's diagonalization argument, we can say that there's an element x tilde which has let's see, x tilde I equals 1 if x1 at I equals does not equal 1. So I just constructed an element in the reals such that it is different from any element, any sequence element. So yes, let's say x, if xi equals 1. In other words, I took the diagonals of x and n and I say that for every element before it, it's going to be different from the diagonal. So this is a very fancy argument. I like it very much. Perfect example. So in other words, since I just constructed an element that cannot be in an enumeration scheme, but must be in the reals, proof by contradiction. Reals are uncountable. You cannot show that there's an injective mapping from the natural numbers to every element of the real numbers. Not possible. Okay, so I've just talked about Baire's category theorem and Meager sets and all the things you can do about that. So let's put that aside until a future date. So now let's talk about continuity. Very important. Many equivalences. There's like 5 different equivalences to continuity. So the definition of continuous is that, let's say the first one, let's say xk is a sequence in M. Let's say as metric space. Remember, I'm just going to talk about metric spaces rather than subsets of metric spaces. A lot of people, when they discuss things, they say subset. But it's really okay because this is a relative. Because this is relatively to that subset, it is itself a metric space. Very important distinction. So, a sequence xk in M and a sequence, and let's say okay, let n equals f of m. Okay. Some people will say let A be a subset of f of m. No. It's okay. It's okay. We didn't talk about them as metric spaces. We don't have to say subsets. It's relative. No. Well, so first thing, a function f is continuous on domain M. So we can always assume that it's surjective. We can always assume that. This is okay. So if xk for any xk that approaches x, okay, we have the sequence f xk approaches f of x. So if a sequence approaches to an element, then you take the function of f xk. Then in the image, there's going to be a corresponding sequence that converges to f of x. So if xk approaches x, then f of xk approaches f of x. Very important definition. So this is equivalent to the more common definition is the epsilon delta definition.